Hello everyone. So today we're going to start on 7.1 iterated integrals. So from 7.2 we learned that we can set what we call a Riemann integral or a multiple integral to try to evaluate volume or n-dimensional volume between a function and between a surface. And the problem is that now that we know how to represent that volume that we're looking for in an integral form, we actually haven't talked about how to actually calculate it. So we kind of know, okay, this is what represents this volume, but we have no idea as to how to evaluate it, because if you think about it, that volume we should be able to represent the volume or find that evaluated volume into a numerical value, but we haven't yet talked about how to do that. So to start that process, I want to quickly remind you that from BC calculus. Okay. From BC calculus, we know that a definite integral can be used to find what we call area under a curve, which is basically the area or the net sign area between y equal to f of x and basically the x-axis, or more accurately referred to as y equal to 0, over an interval from a to b. And if you think about it, this interval from a to b technically would be like our regions of integration in our multiple integral. So a very simple picture would be to illustrate this concept is this right here. So here's my graph, here's y, here's x. So here's my y equal to 0, which is our x-axis, technically speaking. We have our curve, y equal to f of x. And once again, for simplicity reason, I'm drawing y equal to f of x directly over the y equal to 0 line. So that is technically just area, but it could go underneath and it doesn't change the argument, just make the picture harder to draw. So I'm going to just draw it over the x-axis. And here would be the interval from a to b, which is basically what we call our regions of integration, or in this case, interval of integration, integral of integration in this case. And then this area right here, this area is represented by the integral from a to b, f of x dx. Where f of x represents the curve on top, dx represents the differential of x, and it's stuff from a to b. Okay, it's pretty straightforward. So now comes the question, what happens if I now try to figure out how to evaluate if the function f is now two-dimensional? It met from is a function f that met from R2 to R1. So now the domain is not just the x-axis, but now the xy plane. How does that change the way we calculate it? So first of all, recall from what we saw in 7.2, if we let function f to go from R2 to R, let's say z equal to f of xy, then we know that f represents a surface in R3. And let's say we're going to define B to be a closed region in R2. So therefore, imagine the following. So here's my x, here's my y, that's my xy plane, our R2. We can define some kind of regions B, which is enclosed. And if I now take the integral of this thing, would refer to as a double integral. What does that mean is that we basically take the surface of the function f focus on this regions B on the bottom and kind of create some kind of column. Inside these solids. And now we can actually form the volume of this thing using this integral. So the question then will be, how are we actually going to evaluate? So this is the big question. How to evaluate this thing. Because if I know how to write it in a mathematical notation, but if I don't know how to find the answer to this thing, that would be pointless. So before we actually get to talk about that, I do want to talk about this question first. So we will get back to this question, how to evaluate eventually. But more interesting is the following. If I do have a regions B as my region of integration, okay, how do I actually describe this regions B mathematically? I mean, I can draw it out, but that doesn't help if I cannot kind of quantify this region into some kind of mathematical notation. I can't really calculate using the calculation. For integral from BC calculus, it's very easy because it's only one-dimensional, so it becomes just a line segment, technically speaking. But now we actually have to have a closed curve to form the boundary and have the inside of it. So to describe regions B in R2 mathematically, we can do it in two ways. So this two ways would describe every regions in R2. To be fair, in some cases you might have to split up the region into smaller one in order to describe it using these two ways. But for the most part, every region that we're going to be dealing with can be described in either one of these two ways. So what are these two ways? So one way to do it, to describe it, is this. So it really depends on how the regions look like. Then we kind of pick one of these two ways that's easiest for us to actually describe it. So it doesn't come with, like, it's really no particular order. I'm just kind of list them as two different ways. Okay. So first way is to describe the regions like this. So remember, it's a region on the XY plane. Is to describe it by using two different equations. And then a gap between two different values. So here become our regions B. In this case, we can describe B as the following. When describe B to be gap between the following is somehow gap between f of x, or actually g of x on the bottom, between g of x and f of x, and x gap between two different value a and b. Now, and some of you might have a little deja vu from last year, and you should, because this is exactly how we describe what we call area between curves. And now I can also describe this regions a different way, once again, depending on which way fit the regions that we want to, we have to evaluate better. So this here is fit better if you can either to define two curves, one on top of each other, and then you can just get between two x value. But what if the region doesn't confine this way? Then you could describe it this way instead. So instead of talking about two curves that go left to right and one on top of each other, you can talk about two curves that go up and down. When they're up and down, they are called x equal to. So I'm going to say x equal to g of y and x equal to f of y. And for y value, I like to call this y equal to d on the top and y equals to c on the bottom. And so these become regions B. In this case, we try to describe region B as first gap between two different x value, with the one on the right is bigger than the one on the left, and then y gap between two values also. So these are the two different ways that we can use to describe a regions B. And as you can see, in this case, we're describing regions B because in R2, using two different set of inequality, one describe what happened to X and one describe what happened to Y. And you can suspect that if I have to describe a regions B in R3, I would very likely need three set of inequality to do that. So now that we know how to describe the regions B, now let's try to figure out how to actually evaluate this double Riemann integral. So now comes the next and probably most important question: how to evaluate this double Riemann integral over B, f of x, y, dA. So the way to do that is to actually make use of what we learned before. So imagine the following. So I'm going to try to show you how to evaluate this integral using one of the two ways to describe B. So in here, maybe I would describe B. How about we describe B this way? Okay, let's say we have B. And I'm going to say B actually gap between these two curves. One of them is on this side, which is x equal to, I'm going to call it a of y on one side. Actually, I'm going to use b on this side. And I'm going to say this side is the curve x equal to a of y. And then I can say, well, the top point and the bottom point here will be y equal to d on top and y equal to c on the bottom. So in this case, I'm describing regions B to be using x gap between a of y and b of y, and y gap between c and d. So I'm using actually second way, which is this one right here, way number 2, to describe this region. Now, this regions right here can actually be described using first way also. In that case, I will probably break down on the left and the right side and have a top curve and a bottom curve in here, but I choose to do it with a left curve and a right curve in this case. And you'll see why, because I just want my final product to look a certain way. That's the reason why I choose to do that. So now comes the question: how do we actually calculate the volume that we want to do? So let's show you what the picture will look like if I were to evaluate into so let's say here's my surface, z equal to f of xy. Here's z, here's x, here's y. Okay. And let's say here's my regions B. So I'm going to just draw something, I don't know, possibly equal to it. B, right here. And of course, it forms some kind of shape on top. Okay. So hopefully that kind of give you an idea as to how it looked like, the entire solid. Okay, so you kind of cut out a piece on top on the surface and directly over B, and then it formed like kind of like column shape. Okay, so now the question comes down to how are we actually going to calculate this volume? Well, the idea is the following: is to make use of what we know. So what do we know? Well, we know how to find area under a curve. So the question is, how do I use that to help me figure it out? So how about we do the following? So let's see if we can go through this discussion. Imagine I pick a value, a specific value called y sub I. So when I do that, I actually form a horizontal line on the xy plane. Okay, let's call this line y equal to y sub I. And that line would actually form also on this picture right here, maybe somewhere over here. Okay, maybe I can do a little bit better, drawing it parallel to the x-axis. Okay, that looks pretty good. So here's my line y equal to y sub I. Okay? Now here comes the big question. If I look at this line right here on the xy plane, it intercepts our regions B at these 2 points. So what would be the coordinate of these 2 points? Well, actually pretty simple. The coordinate of these 2 points, this side would be B of y sub I, y sub I. And on this one would be A of y sub I, y sub I. So those are 2 points. Okay? Now come the interesting part. If I now look at this line in the picture in 3-dimensional, we already established that this line would have a corresponding curve that go on top into a surface, and therefore also form some part of a curve right on top, that corresponding with the line on the bottom that cross into regions B. And here comes the interesting part. If I now take that, imagine that I can take a knife and cut along the y sub I line, and I open up and take a look, what would I see? I would see the following. Okay. And I would see this line. Oops, actually, no. I will see the line that intercept at these 2 points on this line. And one of them will be the x-coordinate y, A of y sub I, and the other one will be B of y sub I. So that corresponds to the 2 points on the regions B. And they go in the x direction. And there will be some kind of curve corresponding to this surface between those 2 points. So that would actually be this picture right here. Imagine I would draw this straight line down here and down here. And so this picture would be basically this. Okay, I don't know if we mess it up or not, so let's find out. Is this surface right here in the middle. Okay, actually it's pretty good. Actually kind of highlighted. Okay, and that kind of thing right here would be this picture right here. This picture is at y equal to y sub I, and this look a lot like area under a curve. As a matter of fact, you can identify the top of this thing is basically z equal to f of x y sub I, because this whole picture is along the line y equal to y sub I. Therefore, the y coordinate of the function become fixed to be y sub I. And the x still change because moving in the x direction. And now imagine the following. If I now take this area, I can actually find the area of this thing right here. So let's try to find it. So along the line y equal to y sub I can now define this area to be a sub I, and that would equal to the integral from the lower limit, which is a of y sub I, to b of y sub I. And then the height of the function is given by f of x y sub I dx. And that gives us the area under this curve across our regions B. Now, the interesting thing is, what if now I actually give this an artificial thickness so that I can now use that to approximate a volume of this solid, of this volume that we're looking for, through kind of like one layer of it. Meaning instead of looking at this line, how about we kind of form into a thickness? I'm going to call how thick it is delta y sub I, to corresponding with the y sub I. And therefore would actually make this into some kind of into something just like this, into a piece of like solid, like a wall that has some kind of thickness to it. And therefore I can now actually calculate the volume of this thing, assuming that it has a uniform thickness, which I know is not supposed to be, and is also supposed to have a little wiggly on the side, but we're going to kind of make it into more or less like a rectangular prism type thing. Then I can now identify that the volume V sub I would actually equal to A sub I multiplied by delta Y sub I, because A sub I is like the base area, and then delta Y sub I become kind of like the width of this solid. And if this give me a volume of one of these, so now what I'm going to do is simply draw more lines so that I can kind of cut up this regions B. And if I do that, I can then try to form what we call total volume. And that total volume, actually I don't have room here. I'm going to have to move the next line. So then I can now try to form what we call a total volume. And some of you probably already see where this is going, because we only talk about this like 4 times in 7.2. This volume would now be equal to some kind of summation where I can start from 1 to some value n of all these volume v sub I together. Therefore become a summation of I from 1 to n a sub I delta y sub I. And a sub I is given by integral, so I'm going to go and say, well, that's just equal to I from 1 to n integral of a of y sub I to b of y sub I, f of xy sub I, dx times delta y sub I. Yeah, I'm going to put parentheses on this thing so that you can see that is basically what a sub I equal to. Now, if that gives us a total volume approximately equal to this total volume, well, because obviously, you know, it's not going to be exactly the same because our v sub I is actually just approximately what one layer will look like, but I could improve my approximation. And the way to improve my approximation is to make delta y smaller, so that the layer that we're doing is thinner and therefore give us a better fit to the regions B. But doing so, making delta y sub I smaller, will mean that we have to do more of this, and therefore forces this thing to go off to infinity. Therefore allow us to actually define this total volume to be equal to this expression, limit as n approaches infinity, summation I from 1 to n, the integral from a of y sub I to b of y sub I, f of xy sub I dx delta y sub I. And if you're thinking like, wait a minute, that looked like something that we have seen before, you are correct. This is referred to as a Riemann sum. And yes, the Riemann sum can take on many different forms, depending on how you want to use it. One of the most important thing about Riemann sum is that it has to have this delta something at the end. You have to have limits as n approaches infinity with the summation, and then we have something inside that we're going to try to sum up. So in this case, it's tricky because we actually have an integral inside. Now come the big definition. What happened to this infinite Riemann sum? Well, we know that this infinite Riemann sum converges to the volume. And so now what I need to do is create a notation for it. So the notation is this. So this total volume is actually equal to this, an integral from c to d. Remember, in the Riemann sum, the limit and the summation turn to the integral symbol. And then we still have the integral inside that go from a of y to b of y. We drop the subscript now. F of xy dx, delta y sub I become dy. And this expression should define the volume that we're looking for, which means it should equal to the Riemann integral or the double integral that we set up before. Now, this integral has a special name for it. This integral is called iterated integral. The word iterated meaning doing something one after another. In this case, an iterated integral basically meaning that you're doing an integral after another integral. Like the notation look like, it's basically meaning that you integrate and then integrate again, using two different set of limits. Also very important to identify is that this is now defined to be a definite integral. The reason why it's a definite integral because it now have limits set up for the integration, which is a very important characteristic of a definite integral, is that it involves limits. This, on the other hand, right here, this is referred to as a Riemann integral. Or you can call it a double integral. And this is not a definite integral. So not until you actually figure out what the limits are, you actually don't have a definite integral yet. But it does represent a single value. So it does have that characteristic. It's not like an indefinite integral. But it's also not a definite integral yet because it doesn't have the limits. Once it has a limit, then it's now a proper indefinite integral. Now, and also one thing extremely important is the following. One thing that's important is this. Notice that dA in this, based on comparing these two expressions together, dA actually equal to dx dy. Or, because of this multiplication here, dA can also equal to dy dx. Which of these two ways is correct? They're both correct, but there is a difference when you put dx dy versus dy dx. When you do that, you establish what we call collectively an order of integration. Because of the fact that an iterated integral is basically meaning is an integral and is an integration that you kind of repeatedly doing the integration one after another one. That's what the word iterated means. And when you do that, you kind of have to follow some kind of order. The order that you choose is actually not important because by definition, regardless of which order you choose, you should get the same exact answer because regardless of which order you choose, the integral that you set up should equal to the volume of the object. And it doesn't matter which way you do it, the volume of the object should remain exactly the same. And if the volume of an object can actually change based on the way we calculate it, then it will create all sorts of problems. So therefore, we can be sure that no matter which order of integration we do, we get the same answer. However, it does depend on the way we set up our integral. And now notice in here, there are two different orders of integration. And guess what? We have two different ways to describe the regions B. So therefore, it's important to understand that the way you choose to describe the regions B would most likely dictate the way that the order come out. Meaning in this particular derivation, I have dx dy, and it's directly tied to the way I define B. And yes, if you're thinking like, so does that mean that if I define B in using the other way, that would change the order of this integration? And the answer is yes, it does. We will talk more about how the order of integration would affect the way the integral work. Okay, but last thing I want to mention is the following. When you do have dx dy or dy dx, what does that mean? When you have dx dy, that implies that when you're doing your integration, you will integrate, x first, then integrate y. And if you have dy dx as your integration order, then that would mean that you will have to integrate y first, then integrate x. And remember, because both of these directly tie to the way we describe our regions, I can also point this out. This dx dy usually come from regions B, described the following way. The way that we try to describe it, meaning x gap between A of y and B of y, and y gap between C and D. Now, if you want to do dy dx, then your regions B would have to be gap between C of x, is between y, between D of x, and then x gap between A and B. So therefore, don't think that you simply reverse the order of the integration and that would be it. You actually been forced to redefine B in a certain way in order for you to choose the order of integration. Now, for now, you might not understand how this will work, but we will do an example in the next video, and we'll do some example in the next video so that we understand how the iterated integral work. And then we'll also go do some example where we try to reverse the order of integration to show you how to do it and what are the implications of doing that. Okay, but unfortunately, my time is up for this video, so I'll talk to you again in the next video. All right, bye-bye.